All right. Welcome, everyone. Appreciate everyone coming out today. Essentially the first day at reInvent. My name is Eric Dame. I am a solutions architect for Amazon Web Services. Today I have Ram with me from Beeswax. He'll introduce himself in a little bit, and we'll get a little bit of story around Beeswax and how they're using AWS platform. So one of the cool things about working at AWS is I get to listen to customer stories from folks like Ram and Beeswax, as well as understand sort of the cool, interesting things they're doing. So in this talk, we're going to sort of talk about real-time bidding, or RTB, on AWS. And since it's a 300-level talk, we'll assume that most folks know what real-time bidding is and have a decent understanding of the AWS platform. We're going to cover a pretty wide variety of different areas throughout the talk here. But mainly we're going to focus on things like performance, some of the considerations there, scale, what's our global footprint look like, as well as cost optimizations. How can you really keep an eye on your costs and make sure they're not scaling out of control, as well as data, retaining your data, doing some analytics on your data. Where do you store that data for long periods of time? So as a quick heads up, we're going to be passing the baton back and forth here. We're going to try not to drop it, but we'll do our best. And so Ram and I are going to be talking sort of more dynamically, just to give everyone a heads up there. So this is essentially what RTB sort of data flow might look like from a holistic perspective. We're really going to focus on that area there and the red circle. And essentially, just as a quick recap, RTB, or real-time bidding, is really the process of a user goes to a website, they click on the page, and then behind the scenes, there's a series of transactions and essentially bids from different providers happen, and effectively the lowest, or the highest cost bidder or price bidder actually gets to place that ad all behind the scenes. All happens under 100 milliseconds, unbeknownst to the user. And so essentially what we see is customers following a process of ingesting their data into AWS. They need to store or make decisions on that data pretty quickly. So they use something like a NoSQL data store for that generally. As well as how do they run analytics or campaign management? How do they store that data and even run ML or machine learning type models on the data later on? So before we dig in or dive in here, just to kind of go over why RTB on AWS, right? So why would you build your real-time bidding service or platform on AWS? And really, there's essentially 5 main reasons that we've sort of come up with after talking with a bunch of customers. The first is really their pace of innovation. So if you think about today, we have 90+ services on AWS. The one I was talking to Ram earlier, the one bet I would probably make at Vegas is that by the end of the week, we're going to have several more services. So 90+ and counting. Things like network load balancer, which is relatively new, we're going to dive into a little bit more, and how we keep releasing new compute instances and memory optimized instances so you can get really performant capacity from your AWS infrastructure. The other thing is our spot market, right? So pretty unique to AWS, as there's something called the EC2 Spot Market. We'll dig into that a little bit deeper later on. But you can bid on, or you can request really deep discounted instances using the spot market. Another reason is just our global footprint. And so if you look at regions around the world, today we have 16 global regions that are around the world, and this allows you to deploy your infrastructure the same way across, whether you're in India or the US or wherever it may be. Then we have several more that we pre-announced coming online in the next couple years. The other reason is just our broad choice, right? So we want to give customers choice. So whether you're using a variety of our managed services like Kinesis or load balancers or even DynamoDB, or you can run your own technology or a series of technologies on EC2, right? So you can spin up a virtual machine and you can deploy your application of choice on EC2. And then last but not least is our sort of growing ecosystem in AWS. So, publishers like Hearst and Yelp, media companies like Turner and Discovery Channel all have presence in AWS. This gives the opportunity for customers to interact with one another and low latency, as well as for cost reasons within the AWS ecosystem. So with that, I'll let Ram introduce himself and tell a little bit about his story. First one.
Thanks, Eric. Always excited to be here at reInvent. Amazed at the scale of this event and how much it grows year on year. So good afternoon, everyone. I'm Ram, co-founder and CTO of Beeswax. This is a company that I started about 3 years ago with two of my former colleagues from Google. We're based out of New York. We're a global organization. We have an office in London to oversee our European business. We are venture funded. We raised Series A last year, and we have a growing number of customers who are really happy with our product. And our business, the team, and the system continues to grow pretty rapidly. So what we do at Beeswax is that we design, build, and operate the Beeswax programmatic cloud. The programmatic cloud is a fully managed RTB platform built on top of AWS. It provides our customers who are marketers or ad networks with a flexible bidding platform that gives them complete control and full transparency. So in this talk, I'm going to address some of the features of the programmatic cloud, and in particular, I'm going to talk about 3 features of it. First, the programmatic cloud is a fully functional DSP out of the box on day one, and it's on this aspect this talk's really going to be focused on. Second, the programmatic cloud provides our customers with extensible APIs that they could build on top of. And finally, we at Beeswax have partnered with several innovative companies that offer products on top of the programmatic cloud. And so this really lets our customers leverage these deep integrations and really design a custom bidding solution. So the following is the system architecture of the programmatic cloud. Broadly, the system can be broken down into 4 main areas. The campaign management is a RESTful API that lets our customers control their campaign, their budgets, targeting, creatives, etc. The serving component refers to the high-performance, high-scale distributed system that is responsible for receiving and processing millions of requests per second. The user data component is another large-scale distributed system that is responsible for collecting and storing user profile information. And finally, the reporting and the analytics component forms the big data component of the stack. This comprises of systems that process millions of streaming events per second and then convert them into actionable insights for our customers. As is pretty evident from this diagram, we lean pretty heavily on Amazon-managed services. In fact, our operating principle is that we would delegate to an AWS-managed service wherever possible so that they can do the heavy lifting and we can focus on building the product for our customers. With that, I'll hand it back to Eric to talk about performance.
Excuse me. So in this section, we'll talk about performance, sort of I mentioned in the beginning. Ingesting that data, right? Making determinations on that data as quickly as possible. So we'll think about or talk about load balancing, network optimizations, and low latency data stores like NoSQL database or data stores. So when you get traffic coming in at millions of requests per second, it can kind of look like this, right? You have a bunch of different requests coming in. And so, how do you ingest that traffic as quickly as possible? How do you make sure that you're getting that traffic into your system so you can make decisions on that data? So the good thing is we have a variety of different managed services like elastic load balancers for folks to use to ingest that traffic. So whether you're using something like the classic ELB, if you want to manage HTTP or HTTPS, or even TCP traffic with the classic load balancer, you can do so. Or you can choose the application load balancer. So if you have web sockets you need to support, or you have dynamic port assignments you need to do for containers in your backend, you can do so using the application load balancer, or even SSL termination with the application load balancer as well. But the newest sort of offering to the family we're really excited about is the network load balancer. So this is perfect for really low latency, high throughput, millions upon millions of requests per second. And this allows customers to spin up an NLB and not have to think about scaling or even sort of optimizing for the load coming through their systems. So to dig a little bit deeper, NLB really operates at the layer 4 level, sort of the connection level. And what this allows you to do is to pass through traffic very effectively and quickly, as well as you can do end-to-end SSL termination. So actually pushing your SSL traffic through the load balancer and terminating it at your EC2 instance. A lot of folks or customers are requesting to have that sort of end-to-end SSL or TLS connection. You can do so using the NLB. Actually, back to you.
So let's first talk about the need for load balancing in an RTB application. So any typical RTB deployment needs to scale up to 1 million queries per second or so to be able to find the audiences that you need to target. So therefore, you definitely need a pool of machines that are going to handle your incoming request volume. And having a really good load balancer is a pretty indispensable component of your overall stack, because that's going to ensure that the load is uniformly distributed to your pool of machines. In the case of RTB, the bid requests themselves are transmitted as an HTTP request, and the bid request is actually the payload of an HTTP post request. So what this means is that load balancing solutions both at L4, which is the network layer, or the L7, the application layer, are both feasible to be used in an RTB application. So all the Amazon managed load balancing services, such as the classic ELB, ALB, NLB, all three of them could be used in an RTB application. We at Beeswax, though, have chosen to use the network load balancer, and I'll go into the reasons for doing so. The first reason is that it's really fast. It's extremely fast. It's low latency, which means that all the savings that you get at the load balancing layer can be transferred to your application. The packets on the way in are routed by the load balancer to the right instance, because the connections are actually terminated at the instances. And on the way out, the packets leave the EC2 instance and make their way out through the load balancer. And this requires absolutely no changes to the routing configs in the VPC whatsoever. So if you're curious as to how this thing works under the hood, I would encourage you to check out the NLB talk later in this week. The next aspect of NLB that's pretty useful for RTB is that it's pretty resilient to spikes in traffic. It's pretty common in RTB for traffic surges to happen. Exchanges go down and then they come back right up. Sometimes you could have very large campaigns that come online almost simultaneously. And when this happens, there's a pretty big spike in the number of impressions, clicks, and activities coming into your system. So having a load balancing layer that can deal with these kind of spikes is pretty valuable to have. The third aspect of NLB, which makes it pretty attractive, is that it has a fixed IP address. You can assign an elastic IP to it. This means that there is a stable route from the exchanges to your bidder that's independent of the DNS. And this is a pretty big deal, because what we have noticed is that exchanges and the DNS resolvers don't really respect DNS TTLs, and you could have a lot of traffic being lost in case there's a change to your DNS. And with the classic load balancer, for example, when the traffic used to go scale up and scale down, the IP to DNS mappings would change, and the DNS that Amazon set up had a TTL of a minute, and we had all sorts of issues making sure that traffic was routed properly back to our backend. And also, NLB integrates well with the rest of the AWS ecosystem, which means that it's plugged into Autoscale and Code Deploy, et cetera, so we can even leverage those integrations. So the millions of queries per second that hit the load balancer translates into gigabytes of data that need to be transferred in and out of a single EC2 instance. So it's no surprise that RTB is a pretty demanding application on the network. And in our experience at Beeswax, we've found that running your RTB workloads on instances that support Elastic Network Adapter, or ENA, tend to perform really well. And there are a few reasons for that I'll get into. First, ENA offloads checksums to hardware. So what this means is that your CPU is now free to do more interesting work in the operating system or in your application. ENA sets up multiple receive and transmit queues to a network device, which means that all your networking operations can now have true parallelism, because multiple cores could be involved in receive and transmit. There's a feature called receive side steering, that ENA supports in hardware. What receive side steering does is that it routes the incoming packets to the right CPU so that you get benefits like cache coherency, et cetera, which also increase performance a fair bit. And the net effect of all of this is that the interrupt load for receiving and transmitting packets is distributed evenly across your different cores in the machine. And so that means that if you have a multi-core machine, a single core is no longer a performance bottleneck. The following command can be run to see if ENA is enabled on your operating system. At Beeswax, we used Amazon Linux and Ubuntu, and both these flavors of Linux support the ENA device drivers. The goal of the slide was to share some numbers that we see in a deployment at a single region. So we see about 2 million active connections at any given time, and about 2 million new connections being established every minute. In terms of bandwidth, our system consumes about 120 gigabytes per minute. So yes, it's a fairly demanding application on the network, but the combination of NLB and ENA gives us this ultra-performant network that we have come to rely upon, which once again is an example of how you can leverage Amazon to do some of the heavy lifting so that you could focus on building your application. Back to Eric.
Right. So one of the things we want to do is just to make sure, don't just take our word for it, right? So you can actually use this tool. This is actually called Bees with Machine Guns. It's not from Beeswax, but the name sort of fits this presentation. It's actually on GitHub, and it's available at the Chicago Tribune actually developed this app. But what it allows you to do is application or load test your applications using this Bees with the Machine Guns. So you can go to that GitHub site, and actually you can spin up a bunch of EC2 instances. In this example, I'm actually spinning up 100, and I'm doing 1 million requests over, essentially per second, over 10 million requests total. And so I'm actually pointing to the NLB in this sort of example. But don't take our word for it. Go test it up yourself. Again, we're not talking about thousands or even hundreds of thousands. We're talking about millions. Millions of requests per second without any sort of ramp up. It's just instant to the user. So the other thing we touched on in the beginning here around speed or processing is low latency NoSQL data store. So if you're building a bidder or you're an ad tech industry, you need to have some sort of, generally you need to have some sort of NoSQL low latency data store. So something like DynamoDB or Elasticache running Memcache or Redis on top, or even AirSpike to get that, to make certain decisions on your data as quickly as possible. So you might have match tables or segment sort of data or even cookie type information that you want to make sure you match or make a decision on as quickly as possible. So DynamoDB has been around for a long time. It's a NoSQL data store, fully managed. I think it's been about 5 years now it's been around. More recent is the DynamoDB DAX. So DAX is a fully managed cache you can put in front of your DynamoDB store. And this allows you to get from milliseconds to microseconds in terms of latency. So for RTB or even ad tech industry, this is really a game changer in terms of getting that really low latency. And what's really cool is you don't have to rewrite your code. It's just a new endpoint. When you create that DynamoDB DAX endpoint, you just switch that and point your code to that instead of having to rewrite your application. So with that, I will pass it back to Ram to talk about sort of their NoSQL experience.
Thanks, Eric. So data really forms the bread and butter of RTB, and it's pretty important that you have a really good NoSQL data store in your RTB stack because you're going to use it a fair bit. At Beeswax, we rely on AirSpike for giving us this high performance, low latency NoSQL data store. Our application is written in C++, and it predates the announcement of DynamoDB DAX. And once DynamoDB DAX has a C++ client, then it's definitely going to be an attractive alternative for us to check out. But in the meantime, we are managing our own AirSpike clusters. And so this is probably the only instance of a service where we don't rely on an Amazon managed service, but decided to do it ourselves. So based on our experience of running AirSpike on EC2, I'd like to share some of the best practices that we've learned over time. First, AirSpike is a pretty demanding networking application. Again, should come as no surprise. And you see about hundreds of thousands of packets going in and out of a single instance. And so once again, having the ENA enabled instance types is going to help you a lot to improve the performance. The other thing about AirSpike is that it can leverage multiple network interfaces if they exist on your instance. So for example, you could have one instance that's just responding to client requests and another instance that's being used for communication between the nodes in the cluster. And setting up multiple network interfaces on EC2 is pretty straightforward. So it's one of those things that I would definitely encourage people running AirSpike in production to check out. The next thing that we do is that we run AirSpike in a placement group. The placement group is an EC2 feature that enables high bandwidth and low latency between the VMs that are in a placement group. Again, running AirSpike in a placement group improves performance, but you should proceed with caution with this one because Amazon makes no guarantees about the availability of a capacity, of your instance type or whatnot in a placement group. So you could end up in a situation if you have to scale out, you just don't have capacity in the placement group. So use this carefully. And finally, user data profiles tend to be pretty large data sets that storing them and serving them out of memory can become very, very expensive. Fortunately, Amazon has a solution for that as well. They recently announced, last year actually announced this instance type, i3 instance type, which come equipped with a NVMe SSD drive. The nice thing about these drives is that they offer very high performance at a fraction of a cost. So all of a sudden, it's okay to be able to do reads at serving time from SSDs because these SSDs are able to handle the high throughput as well as the low latency requirements. So definitely, if you're running AirSpike in production and you have large data sets, do check out the i3 instance types. Handing back to Eric to talk about scale.
All right, so in this section, we'll talk about our global infrastructure, as well as this notion or this concept of building in pods or within regions. So as mentioned before, we have 16 regions today. This is sort of what the map of our regions look like. We have a variety of different regions coming online in the future, things like Sweden, Hong Kong, as well as other areas that we pre-announced. And so just to be clear about sort of our regions versus availability zones, and how we design them. A region is essentially a geographic distinct location. And within those regions are availability zones, which could be one or even many data centers that are linked together over low latency fiber to get you that really low latency really low latency connection between those AZs. So the other thing that we sort of encourage customers to do is to deploy your applications across these AZs to get the fault tolerance as well as the high availability and really to be able to scale your application much wider, much greater than you would in a single data center sort of scenario. So the other sort of notion of, as I sort of mentioned, is building with pods. So even though we have distinct geographic locations around the world, you can actually build your application within this idea of a pod. So each pod can be a region, and then within that region, you have your own infrastructure, your own auto-scaling groups, your own application groups, as well as isolates from failure into one region. And you don't need to spend a lot of cost or sort of engineering time developing data transfer or other sort of engineering overhead to figure out sort of how do I cross traffic across these different globally distributed regions. And one way you can do that is using global DNS or Route 53. To sort of point your traffic to different regions depending on latency or even regional sort of constraints. So I'll pass it back to Ram so you can talk about sort of their deployment strategy and model.
Thanks. So at Beeswax, we deploy across pods by using this tool that we've developed in-house called Hive. It's a Beeswax system management tool. One of the cool things about Hive is that it abstracts away the details of how a Beeswax service is actually implemented. So it could be running as an autoscale group or as a container on ECS, but all that is abstracted away from the operator of Hive. And it supports common tasks such as creating resources, supporting deployments, etc. It's been written in Python, and it leverages this amazing Boto 3 API. Which means that all of a sudden we have access to all the cool features that IAM offers natively for access control, etc. And so we're able to get this ability to be able to deploy globally without having to set up any infrastructure, because Hive just relies totally on AWS APIs. Under the hood, Hive relies on CloudFormation templates extensively. We will usually, our practice is to set up a template, test it locally on a single pod, and then easily replicate it globally across the different pods. So whenever you're running a global application, such as RTB, there are certain things that you have to keep in mind that naturally occur by running a global service. So for example, a concrete example of that is that if you're running an application in Europe, you have to comply with EU regulations. So an example of an EU regulation that you have to comply with is that if requests originate from browsers or devices in Europe, they should be routed back to servers in Europe. And for this, we've come to rely on an Amazon-provided global service called Route 53 that has a feature called geographic routing that just takes care of this for us. So it's pretty easy to set up geographic routing, and once that's set up, then it's guaranteed that you're compliant and that requests that originate from EU always go back to servers in EU. The other feature of Route 53 that we leverage a fair bit is latency-based routing. So what this feature lets us do is it ensures that we can always route our users to servers that have the lowest latency path to them. And note that this is not the same as the shortest path. The shortest path could have all kinds of issues in the network at that time. So the Route 53 global infrastructure is constantly working behind the scenes and making sure that it always has the most optimal route from the user to the servers. And leveraging this means that we're able to reduce discrepancy between the impressions, clicks, and activities that we report and the exchanges report, which is, if those of you are not tech, it's a pretty big problem. And finally, complex routing scenarios, which are a combination of the two that I just described, can be easily done in Route 53 using traffic flows. It's pretty easy to set up. So RTB is a global application. And so if you're working with big advertisers, it's pretty common for them to be running campaigns that span multiple regions or continents. And so it's really important for your bidder to be able to synchronize state across regions. Examples of the state could be campaign management data, budget, user to user profiles, cookie matching, frequency capping, tons of state. And so one of the things that you'd need is a reliable and a secure global network that connects your regions. Fortunately, there is an AWS-provided solution for this that's called the Transit VPC. The Transit VPC is basically a hub and a spoke model where the Transit VPC becomes the hub, and the VPCs where your services are operating become the spoke, and all the packets are routed from the spoke via the hub. You could have a couple of Cisco routers running in your hub, and the connectivity between the hub and the spoke itself is secured via an IPsec tunnel using Amazon's VPN. And again, this is a fairly simple thing to set up in practice because Amazon provides a CloudFormation template that you could use and customize to set it up for your needs. With that, I think I'll hand it back to Eric to talk about cost.
All right. Thanks, Ram. So we talked about ingesting data as well as our global footprint, but how do you make sure your costs don't sort of overrun? How do you make sure that your costs are staying proportional to your business needs? So we'll talk a little bit about some cost considerations when you're building a real-time bidder. So this could be sort of a typical traffic pattern. Could be users around the world coming online at different times. So your traffic's going to go up and down. Or you might have seasonality with your application. And so you're going to have fluctuation in your demand. So the one thing we encourage is for customers to scale out, but also scale back in, right? So when your demand goes up, you scale out your instances. When your demand goes back down, you scale back in. That's where you get that nice sort of savings there. And you're really matching your compute capacity to your demand. So how do I do that, right? So one simple sort of way to do this is use something called auto-scaling groups, or ASGs. In this example, all we're really doing is we're going to create a load balancer, whether it's an NLB, ALB, whatever it may be. We'll attach an auto-scaling group to that. And then we're going to trigger based on a certain metric. So whether it's CPU or memory, or even a custom sort of defined metric that you create, you can do so and trigger your scaling out. And so once that alarm fires, that metric is triggered, then you're going to add one or even many instances to your auto-scaling group to effectively grow out your demand as your demand increases. So right back to Ram here to kind of go over how they're using auto-scaling.
Thanks, Eric. Okay, so one of the things I wanted to show via the graph on the screen is that, and this is a real graph in production, of how predictable RTB traffic is. As you can see, there's a very clear pattern in a given region where traffic surges up during the day. There's a peak at around 8 p.m. when folks go home, and then there's a lull when folks hopefully go back to bed. And that's represented by the green lines, and then the blue curve shows how at Beeswax we're able to leverage autoscaling to make sure that the number of instances that we have in service closely tracks the incoming load. And so we're able to both scale up as well as scale down effectively. And so I wanted to share some of the best practices that we follow at Beeswax based on our experience. So one of the things that we've come to realize is that CPU is a pretty good metric of the load coming into the system. And so if you set up an autoscale group with CloudWatch alarms that trigger scale up and scale down actions based on CPU threshold, that tends to work pretty well. Also, we leverage this feature of autoscale called schedule actions. And what this lets us do is pre-warm and keep our instances ready, because as you can see, the traffic pattern is pretty predictable. And so we could have instances ready, waiting for the load to come in just before the early sunrise traffic hits our systems. It's a very useful feature. And also the last bit of best practice that we've learned over time is to really optimize the boot times of your bidders. So make sure that the AMIs that you're using for your bidders have all the libraries and software pre-configured so that in case there is a spike in traffic, you can quickly ramp up capacity and have your bidders up and running very quickly to be able to handle the spike. Back to Eric.
Great. So one of the key takeaways from this presentation, we wanted everyone to ensure they sort of, I guess if you remember one thing, it's the EC2 Spot Market. So the EC2 Spot Market lets you get deep discounts for your instances. Effectively what it is you're bidding on excess capacity in the EC2 fleet. So there can be fluctuations in the price, but normally you can get up to upwards of 90% off on-demand prices. So our sort of data or our interaction with the customers, especially around the ad tech customers, has shown that a lot of them rely heavily on the spot market to really reduce their costs as they scale. So there's a couple ways you can use spot, right? So you could say I want to pay a certain price. You specify the amount of instances you want, and then you specify the type of instance you want. And then you can say I want N number of instances, and you're good to go. Or you can use something called Spot Fleet. Spot Fleet allows you to mix and match instance types. So you can have C instance types, Ds, Is, whatever you want. And then let's say you specify 100 instances, and you could say, hey, I want to make sure I have 100 spot instances running at all times. So you create a Spot Fleet for that. And then if there's an instance that terminates or goes down, it'll reintroduce or relaunch an instance and put that in your Spot Fleet. So you're constantly getting essentially around 100 or whatever your configuration is amount of instances. The other way to do it is use something called spot blocks. So if you need an instance that is sort of alive or there for at least 1 to 6 hours, you can specify that in your configuration. So maybe you need to run a job and you want to get that deep discount, but you want it there for 4 hours. You can specify that using spot blocks. One of the key sort of pieces here, right, is that since you're bidding on excess capacity, and the price for that excess capacity could change, you could run into a situation where you pay a certain price for an instance, and then that price actually increases, and therefore we'll actually come in and terminate that instance, but we'll give you a 2-minute warning. And so customers can use that time to evacuate the instance, move whatever state information they may or may not have on there, or even spin up another instance, like an on-demand instance or another spot instance. So this kind of lends itself to workloads that are stateless, right? So if an instance fails or goes away, it's not a big deal. You just spin up another one. Or workloads that aren't time-bound or even batch process type workloads. Or you can kind of try or use a pattern like this. One of the cool things about this is that we're sort of calling it the Waterfall autoscaling group. And so what this does is you're creating a load balancer, and then you're actually using an on-demand autoscaling group and a spot autoscaling group. So you get that reassurance of having on-demand instances, and then you're actually getting that cost reduction in performance from using spot instances. So essentially what we're doing is we're going to create 2 autoscaling groups, 1 spot and 1 on-demand, and fluctuate depending on traffic. So from a configuration perspective, it might look something like this. This is an autoscaling group. We have 2 CloudWatch alarms or metrics we're going to alarm on. This is the on-demand group, and we're going to alarm on 80% threshold, and we're going to scale based on 80%. And then we're going to reduce or scale back in on 40%. So we flip over to the spot autoscaling group. We're going to sort of stagger it. So we're actually going to scale on 50%, and then we're going to scale back down on 20%. So essentially, we're sort of staggering the spot and on-demand usage. And effectively, what we're trying to do is spin up as much spot as we can, but to get that assurance of having on-demand. So if our application needs to scale, it's going to trigger spot first. And then as it scales back down, it's going to kill on-demand first, and then it's going to kill spot, but actually preserve that sort of on-demand, so you always have that reassurance. And then with that, I'll pass it back to Ram, talk about how they use Spot.
Thanks, Eric. All right, so if there's one thing that you can take away from this talk, it is that please go and check out Spot Market. Because if you're running an RTB application and you're fielding millions of queries per second, it's going to be a very, very expensive service to run. And if you care about operating costs, which I'm sure all of you do, Spot's going to save you a ton of money. So definitely go check out Spot. At Beeswax, we've been using Spot for a pretty long time, and here are some of the best practices that we've learned. The first thing is to make sure that your bidders are completely stateless. So if there's any in-memory state that your bidder is building, then make sure that the state is persisted on hopefully an Amazon managed storage service like S3 or EFS. This will ensure that even when a Spot instance is terminated, there's no data loss because everything's present in a cloud-based storage. Next, if your bidder is performing any kind of operation that needs to be logged, like for example, you typically want to be logging all the bids that your bidder is making, then make sure that that is also persisted into an Amazon managed service such as Kinesis. There is obviously challenges at trying to log bids at millions of queries per second. So at reInvent last year, we gave a presentation on how you could leverage some of the features of Kinesis to be able to do that effectively in a cost-effective manner. And also, Kinesis provides this library called KPL that I'd encourage everyone to check out that you can really use to be able to log everything into Kinesis effectively. And so the one thing, the golden rule you should follow is that absolutely no useful information should be persisted onto the disk in the machine itself, because you know what, Spot instances just go away. The next best practice is to minimize the boot time of the bidder. This again, as I mentioned during the autoscale section of the talk as well, is just in general a best practice to have. One of the risks that we run with deploying on our service on Spot is that capacity could disappear with the 2-minute warning. But this can be mitigated easily by following patterns such as the Waterfall autoscale that Eric described. But in order for that to work really well, you need to make sure that your bidders can come back online on the on-demand autoscale group pretty quickly. And one of the ways to do that is to make sure that your AMIs have a pretty small boot time. I'm going to talk about data.
So we talked about processing, ingesting data, making decisions on the data, as well as cost considerations. But you probably want to keep a lot of that data for longer periods of time, historical reasons. Maybe you want to do trend analysis or other sort of analytics and insights into your data. So we'll talk a little bit about some of those options. So that's a data lake. If you have lots of data coming in, maybe you have data from your bidders, your advertisers, as well as third-party data that you want to ingest and put together. You can do so using something called a data lake, right? And that way you can give access to different users, as well as data scientists or other sort of internal employees, not have to worry about scale. And so one of the key sort of pieces where most customers use is they use S3 as sort of their data layer or data storage for building a data lake. What's great about this is you don't have to copy your data a bunch of times. You can natively use other AWS services. So if you're ingesting data sort of from Kinesis, you can actually point that using Firehose directly to S3 and not have to ETL or do any sort of other programming to modify that. And then you can actually query your data using something like Amazon Athena. So Amazon Athena will let you essentially run SQL compliant or ANSI SQL compliant queries against your data in place without having to move it or copy it or do any sort of ETLing on it. So, why use S3? S3 is a pretty popular service. It's been around a long time, and it's super scalable, right? So if you have 100 terabytes today, you have 100 petabytes tomorrow, you don't need to worry about scaling that up. You don't need to worry about deploying new instances or storage machines or whatever it may be. It just scales as you grow. You also don't need to worry about running compute instances to keep up that storage, like HDFS or having any sort of storage or any sort of compute instances to manage that storage. As well as you can run things like big data frameworks, Spark, Hive, Presto, or even proper Hadoop jobs against that data without having to move it and just do it directly on S3. So another good thing about S3 is there's a variety of different classes, storage classes or tiers. And so S3 standard is the commonly used one, but we also have infrequent access or SIA, as well as even Glacier. So if you think about ingesting your data and actually keeping that data for longer periods of time, that sort of the data gets from being less hot or less accessed and gets a little bit colder. So you can actually write something called or configure something called a lifecycle policy and actually move that data across the different tiers. So you're getting a nice sort of cost benefit for your data as you keep data for longer periods of time. So a typical scenario we see a lot of ad tech customers or even customers in general do with their data is that they have a bunch of data. They want to enrich that data. So again, maybe they have a third-party data set, or maybe they have a variety of other sources that are getting data in. They want to enrich it and combine it. And then they want to give that data set to another user, or they want to actually run some sort of machine learning type models on that data. And so using a variety of different tools or sort of analytics options on AWS, a lot of customers will ingest that data into S3. They'll run it through Amazon EMR, which is our managed Hadoop offering. So again, you can run a proper sort of MapReduce or Hadoop job, or you can run a Spark job against that data and enrich the data with other different sources. And once you've done that, you might want to run some sort of business intelligence tool like QuickSight. So I want to visualize that data. I want to give that data or make a dashboard for other users to consume so they can get insight out of that data as well. And so you can do so using some of the native services with AWS. So with that, I'll hand it back to Ron to sort of talk about their data flow.
Thanks, Eric. So the following diagram is the data-centric view of the Beeswax platform. So I'm going to talk about this architecture left to right. So on the extreme left, we have the data collectors. So the examples of that are the high-performance, high-scale collectors that collect bid requests at hundreds of thousands of queries per second. And the challenge really there is how do you scale up that collection process. And then in addition to that, we have collectors that collect events such as clicks, impressions, etc. And the challenge there is to be able to do the collection in a lossless manner because this is the data that's eventually used for billing. All the data that is collected by our front-end systems are persisted into Kinesis. We use protocol buffers to encode the actual payload of the data that goes into the stream. So moving on to the next section, The streaming message hub is sort of the core component of the overall architecture. This is an autoscale group, again, deployed on Spot instances that is responsible for consuming the data from the Kinesis stream. And we expose a RESTful API to our customers that allows them to configure both the destination of where this data should be routed to, as well as any kind of transformations that they would want to perform on the data. So an example could be that customers might want to transform the data to JSON or CSV or custom CSV with their own headers. All of that is supported through our RESTful API. And in terms of delivery destinations, we support routing to a customer's Kinesis stream, their S3 buckets, or they can even route it to an HTTP endpoint that they have configured to just receive this in a streaming manner. So all the data that's interesting to us is collected by the message hub and then transferred into a bucket in S3. As Eric mentioned, our data lake is built on top of S3. We leverage S3 as the storage layer, and we leverage the Glue metastore to store all our table definitions, partitions, and all of that ends up over there. And we have jobs that periodically transform the format of the data from CSV to Parquet, which is a column IO format. And all of a sudden, it's possible for all this data to be easily queried through systems such as Athena for all kinds of ad hoc analysis. The data lake also feeds our ETL system. Our ETL is built on top of Redshift. The ETL layer is responsible for doing joins, as well as performing aggregations to compute the total number of clicks, impressions for different campaigns. The orchestration of the different SQL queries that need to run on Redshift is done via AWS data pipeline. And we expose the Redshift cluster where the ETL happens for serving as well. But this is fronted by our API that aggressively caches the most common queries. And we've seen in experience Redshift does pretty well when it comes to even serving some of this data. For optimization and analysis, we once again rely on Amazon managed EMR services that ingest the data from the lake, and all the model training and model building happens on our EMR, and then the models are pushed into S3 from where the bidders then pick it up to do interesting things like click-through prediction, etc. So all the data that's consumed and processed is finally exposed to our customers in the form of RESTful API, where they can view how their campaigns, etc., are performing. We've also built a UI on top of this API that really helps them visualize how things are going. And this campaign management framework and the performance reporting framework, both the API and the UI for that are implemented as Dockers that are deployed on top of ECS. And the other use case, in addition to performance reports, is that it's easy to get actionable insights on your data once it's been ingested by Kinesis and once it's in the data lake. So one of the things that our platform does is that it in real time sends this data to a MetaMarkets endpoint that we have set up. And once the data is in there, then you have access to the MetaMarkets UI through the Beeswax portal. And all of a sudden, this allows our customers to have very useful, actionable business insights on the kind of inventory that's coming into the Beeswax bidder, so they can figure out if they're bidding on the right ad sizes, if they're looking at mobile requests, etc. So all this is easily possible and easy to scale. Mostly because we leverage Amazon managed services to do all the heavy lifting so that we can focus on all the good stuff of building our product. And back to Dr. Evil.
Yeah, I think Dr. Evil said it best. Using AWS to power your real-time bidding service will give you over 1 million requests per second. So with that, we blazed through this one, but if anyone has any questions, I think there's mics on either side. Probably the easiest way to folks come up to the mics. And thanks everyone for coming.
Thank you, everyone.
Appreciate it.